And another day we're gonna look more at all we have done at this normal distribution and worked with it a little bit, and we'll just keep working. So I'm gonna select another exercise and do it for you to refresh the whole process. So how about, let's say, number 10, I think is interesting. Exercise 10. Random number generator. So I'm not sure if I discussed the random number generator with you, but turns out that you can produce this type of numbers, and you can put any restrictions. Like, for example, you can set it to produce numbers between 0 and 1, or you can say just produce any numbers. So the exercise is not about producing numbers. It says that mean has to be 0.5, which is intuitively does make sense, because if you start to produce some numbers on the interval 0 to 1, and if anything is possible, 0.2, 0.9, whatever you just can think of, then what you will expect will be the average, right? The average in the center is 0.5. And if you expect to get 0.1, that means it's skewed to one of the directions. So it has to be symmetric. It has to be normal, in other words. Normal distribution and the mean and standard deviation are given to us in here. Of course, standard deviation is definitely not obvious. It's 0.289, but there are ways to actually calculate it. So mean and standard deviation they gave us. And an interesting story. So they wonder, what about the probability? Well, probability we always call as P, and the probability that their mean is greater than 0.57. So X is more than 0.57. Let's say, okay, you're talking about their mean. Yeah, but it turns out that when you deal with the normal distribution, and if you remember, we discussed last time the new formula for the z-scores that was not just fraction x subtract mean and divided by a standard deviation, but we actually went one step further. We went to use a central limit theorem. So we actually divided it by a square root of n, the standard deviation. So that was involved with a sample size, and that's why the x-axis ended up to be not just the axis of x's, but averages for the samples of size n. So if you were to select sample size 100, then if you calculate the averages, so you take the sample size 100 and find the average in that particular sample, whatever it's going to be. When it says not 0.5, well, it may differ a little bit because you take another average, another average, another average for another sample, another sample, another sample of size 100. So for all those samples of the size 100, you can find the averages, and that's how they call not x-axis as axis of the averages, actually. But what they care about is to say if the actual average has to be 0.5, what if it happened that the average is more than 57? Is it possible? What's the chance of this to happen? What's the probability of that? So what's going to be the area, in other words, for that interval? So that's how it works. But I was just trying to explain to you why this is really dealing with average. Why the word that they produce here was averages, that they're mean. You probably wouldn't even notice that, but that's where the word mean is coming out. But anyways, what if x is greater than 0.57? So we used to do the same procedure for all of these exercises. We were to locate corresponding z-square, right? So we have our new improved formula in here. And then I will be, of course, plugging the numbers in. Carefully do that. Just want to make sure that I set this first, right? So I'm gonna have this as a fraction with, so technically it's that 0.57, and then I subtract 0.5 from it, and then divide by standard deviation 0.289 over square root of 100. So that's what we were doing last time and the time before last. So I hope this is something that one starts to get used to. And also we need to make sure that the entire denominator is placed inside the parentheses. So the advantage of using that scientific calculator that shows everything on its screen. So scientific calculator, Desmos. Let's put in this red subtraction statement. So from 0.57 subtract 0.5. Well, sometimes you feel that you can do some of the calculation yourself, and that's good. You can do it yourself, but advice is still make sure you write it down carefully, and then make sure when you plug in a calculator, you do it carefully, right? So it looks the same exact way that I have to do. So now I got the hundredths, right? Point, so right here, 2.42, right? Because the following digit, the digit that follows that 2 is another 2, less than 5, so I leave it as 242. Great, we now need tables. So let me get the tables. Triola table. already here. Let's see. Used it so many times. So Trello tables, we find the column under 0.02 because it's a place of hundreds, right? So I need to go for the 0.2 for the column, and the rest will be my row. What's going on? Why isn't it open? Well, it opens. So let's move to the middle of this, where my positive z-scores are, to that portion of the tables. And so this is negative, here's positive. So we now can go for 2.4 as a row, right? And the column is 0.2. So our answer is 99.22. So this is the area from the left as usual, right? 99.22 is the area that we'll use to find my answer. So the answer is going to be subtraction from 1 to get the other side tail. So from 1 I subtract that 0.9922. And we got the answer. So we have 78 with extra 2 zeros in front. 78 ten thousandths is our result. So pretty low result, right? Very low, less than 1%. Remember, we're always comparing it with 1%. So is this really possible that something with such a low level probability is going to happen? Why or why not? Well, less than 1% is no chance. It is not possible. So to get the average, not 0.5, but way higher, well, it's not way higher, but it's still quite far away from half, is unlikely. So it means that generator that generates random numbers for you is not doing it correctly. So someone was messing up with the generator. So you should get average 0.5, right? But again, doesn't have to always be 0.5. It could be 0.51, maybe 52, but 57 is already very high, too high to happen. The chance of that is very low, less than 1%. So it is unlikely. See, we can test such things as mathematical constructions, generators. So we can test anything. It's very interesting, right? Yeah. Again, very useful. So what I want to do is move to the next section here, which is the last section of the chapter that refers to binomial distribution. Remember the one with those two special formulas, NP and square root NPQ, the one we discussed a little bit in the previous chapter. So the z-score for it is already here. And say sigma, but now no square root of n. Yes, because that's for binomial distribution. Turns out sigma already has square root of n as its part. You see standard deviation. So we don't need to worry about that case. But there is a little extra to worry about, so we'll discuss that. So let me just take an exercise because it's really analogous procedure that is being used, but with extra case that they want to discuss. So How about exercise 1? To start, that says probability that more than 15 people in prison for removing caution labels from pills. Why would they do that? So here we're discussing only setup. So they want to know probability that X is more than 15. I say, well, Alex, I need to know a little bit more information. I need to know mean standard deviation to be able to produce the one process that we had here. So we need to know these two things to get a z-score. No, we don't need to do that in this particular group of exercises because they say just do so-called continuity correction, which means that first of all, you work with binomial distribution. Remember, binomial distribution deals only with the whole numbers, like 15 people removed late. Or there could be 16 people that removed label, or 17, or 14. So we don't have any fractional number of labels removed. We can have either 15 or 16, which is larger, or 17, so forth. So more means to the right. And turns out the number that I need is going to be in between of 15 and 16, which is 15.5. And that's what's called continuity correction. So I need to always write this with 0.5 increment. So X needs to be more than 15.5. So they actually spell this out. So 0.5 is supposed to be added. So more means you need to move to the right by 0.5. So it's actually 15.5. Again, that's definition of so-called continuity correction. And they do this in order to be able to approximate your actual binomial distribution with bell-shaped normal distribution. So notice that this is a little bit not exactly the bell-shaped curve. This is really in the form of bell-shaped curve, but some pieces are above and some pieces of those rectangles are below. So why are there rectangles? Well, because when we calculate probabilities for binomial distribution, we can either have 16 or 15, so the whole number. So they, turns out, come with rectangles if you try to make a picture. I think they have a nice picture. I saw it here somewhere. Where's the picture? So the continuity correction could be shown in such a way that makes more sense. So it turns out when you have various distributions and produce histograms, then usually the histograms look in the shape of normal distribution. We can say it does not look here. Yes, but turns out if you have large enough sample size, and we talked about n more than 30 last time, right? So if you don't just take 7 or 9 entries, but lots of them, then they build as the normal distribution, which means more probabilities toward the center than towards the end, towards the left and the right end. And that's what makes me see that I could use all this stuff that we already saw in chapter 5 for binomial distribution. Turns out that's the idea. So that's why this so-called continuity correction is being used to help me to convert my binomial distribution to the normal distribution. And where's the definition of continuity correction? I'm just browsing through trying to find it. And here it is, continuity correction. So maybe I can clear the mess real quick. So I'm going to share this again. So, share. So you can see the definition that says the either subtract or add 0.5. It depends on the question. So my question I just did was asking me greater, strictly greater than 15 labels, more, okay? So I say it's more than 15.5. Well, what if I try part 2 or exercise 2 that says the at least, so X is at least. What does that mean? At least 24. Well, how is it compared with 24? It means it's not less, maybe greater, maybe equal. See, it is a little bit different because equal is also possible. So what I need is analogously think about rectangle that has 24 and two others that surround it, 25 and 23. And turns out that now I have to decide what is included and what is not. Equal to 24 is possible, which means that I can include this rectangle, as well as greater means keep going to the right. So I don't care how far to the right, I care what the border, what the cutoff supposed to be, and it is 23 and a half. You see, it's always going to be 0.5 when you have continuity correction, but it depends. If it is included, well, then you kind of start on the left. And if it is not, like in the previous example, it was starting on the right. So that's the point. So we now be able to use our approximation like we did in the previous part of the story, but now we have to use 23.5 instead of 24 because the result is going to be a little bit different. And that's what they're trying to get across. So let me say, how are you going to use it? Well, I guess I need to move to the exercises where they actually give me a little bit more information, and I can try to do one here. And for example, if I try exercise number 14, 13, I don't think 13, some people may say, Alex, that's dangerous number. So, okay, I'll start with exercise 14. That talks about find the probability of getting more than 55. So X is greater, right? No equal sign than 55. So that's what they want. And the story that we already saw before, so probability that the baby boy or baby girl was born is 0.5. So they're talking about girls. So that's probability of a girl. And then Q will be then probability of a boy, which is also 0.5. P and Q, remember when we have 100 births, So sample size is 100. We repeat experiment 100 times. Birth of the baby, same experiment, and the chances it's a boy 50% and a girl is also 50%, 50-50. But if you try to get probability that X is greater than 55, and if you try to do it by hand, you're gonna need to spend lots of time, because then you're gonna need to get probability of 56, more than 55, and 57, and 58, and 59. That's what we used to do back in chapter 4, in the previous chapter. So all the way to 100, right? Because more than 55 girls means, well, anything that you could get bigger, and looks like there'll be like 45 or 44 probabilities to calculate. And we had a formula, remember, combinations, P, Q. That's why, to refresh your memories, I also introduced Q. But it's going to take a while because we're going to have to do more than 40 calculations. And that's why, instead of using the binomial formula from the previous chapter, we say we want to use the probability corrections. I need to decide what to put instead of 55, what 0.5 increment to use. So it looks like if I have 55 here, and then 56, I need to see where's 0.5 supposed to be placed. And if that's 54, then making a picture of greater than 55, just like I did in the previous little exercise. I see that our borderline is here. It's in between of 55 and 56. So it's going to be 55.5. So X is greater than 55.5. That's the continuity correction. So I don't go this route. I need to use 0.55. So now I utilize normal distribution, and instead of X, I put 55.5. So I'm able to use the method of this chapter 5. In other words, I'm gonna get a z-score. I think I need to get some, include this. So I need to go for the color, so we can nicely see this. So corresponding z-score, this value of X, whatever it's going to be, and then we'll be able to use tables just like we did in the exercise I started with today, and get the answer. So we approximated the binomial with normal. As long as our sample size is large enough, it is definitely large enough, then we can do that. So z-score, xi minus mean over standard deviation is what I'm using as usual. So mean was NP, and standard deviation for the normal distribution for binomial distribution is square root NP. So I'll plug everything into this formula, all of these numbers. So my 55.5, you see, that's why we have a little extra in this section. N was 100 times P, which is 0.5. Okay, so this is numerator, and then for denominator, I have a square root NPQ. So that's 100 multiplied by 0.5, and then again multiplied by 0.5. I can say, Alex, at some point it starts to be annoying, there's z-scores and everything. Yeah, but just bear with me, I guess. We'll do maybe one more exercise just for practice, and that's probably going to be good enough. So let's try to use the calculator. So as usual, I use my favorite Desmos. So 55.5, right? 55.5 minus 100 times 0.5, or half of 100, which is 50. Well, don't forget, use parentheses around this. So we're now going to divide, and it's square root, so I don't need parentheses. About this argument, just multiply 100.5 times another 0.5. So we have the answer. It's 1.1. See this, 1.1. So we have a z-square, and this is just great. We have 1.1 or 1.10. So we'll be able to use our tables. See, the process is the same, and our goal from now on will be the same. Convert to the normal distribution. So you can use the tables and you can find the probability, because otherwise you would have to do it for a long time. So I need to now go for my tables. Let's do that. 1.1. And it's actually 0, right? 0 hundredths. It's my first column. 0.00. So 1.1 is right here. Next to it is 0.8643. This is area to the left of that number, 8643. And what I need is to subtract from 1. Okay, subtract from 1 and see what the chances for this to happen is going to be. So it looks like it's going to be 7 at the end, then 5, then 3, and then 1. About 13% chance that you're going to have more than 55 girls. Remember, this problem was about childbirth, and the exercise was saying estimate the probability of getting at least, no, it was 13. Oh, actually I did 13. I was trying to do 14, but I did 13. So, well, you can try now to do 14 yourself if you feel like it. So more than 55 girls, well, chance is about 13%, 14. So maybe it's possible, 14%. It's kind of questionable, right? Not very high chance, but possible. That's the exercise. What I want to do is actually find the exercise that I can do both ways. This new way using normal distribution, as well as the old way using method of chapter 4 to be able to compare our answers to see how much of our continuity correction will take us to. So if I can, I think if it be exact the number, that'd be 143. So they just, so as usual, there are all kinds of stories, and some of them look familiar, like cell phones, and brain cancer, or American Airlines flights. So I'm just trying to find exactly when they asked me to find 10 or 20. So those are ones I could do with use of formula, because otherwise, if they say like American Airlines flight 21 or fewer, or women 21 or fewer, so it means 20, 19, 18. So you have to repeat this calculation so many times. So it's going to be kind of hard to do 19 times, right? No, time consuming. That's what I'm trying to get. There's batches and defectives, and it says at least 2 defects found. So maybe that's the one I can do both ways. Exercise 26 is what I'm looking at right now. Acceptance sampling. So the procedure of acceptance sampling was already done before. The one that is usually happens when the purchase of large quantities is being done, and then they decide to test if those elements are good enough or too many defectives. And they say if they have at least 2 defectives, well, they don't want to have it. There's too many defectives, right? So they want to have less defectives, ideally no defectives, but well, defectives happen. So I'm talking about exercise 26. So they say that the company buys bolts in batches of 5,000 and reject the batch if when they sampled 50 of them. So in exercise 26, they don't test all of them, they just test 50 bolts that they purchased and see if they find lots of defectives or not. And now they say here that the rate is 10%. So the chances that they have defective is 10%. So we already know that what we expect is NP, the mean, which is going to be 5 defectives found. So one can say, oh, when they get 50, they expect to find 5. And they say, if at least 2 found, they're not going to accept. Well, so we can right away intuitively say that probably it's going to be way more than 2 because it's 5. So, but they ask us anyways, what's the chance that number of defectives will be more than 2? It's probably pretty high chance. But let's find out let's calculate what this chance is. So the old way, we would say, is either going to be a probability of 3 defective, as they say exactly more than 2, or at least 2. Oh, at least 2, not less. So it's greater than or equal, right? So it's probability of 2 or 3 or 4 or 5. And say, so you're going to calculate all these probabilities? No, I'm going to use complements. That's what we did before. So we go 1 minus probability that we had less than 2. So this way I can approach this calculation from the other end, right? And when I approach it from the other end, I'll have to just calculate twice. Less than 2 means I either care for no defectives or means plus, right? Or is always plus, one defective. So that's what I can calculate. And P is here. Q is complement. Always find by subtracting from 1, right? So it's subtract 0.1 from 1, which is 0.9. So I could use that formula, probability that we have X defectives is going to be combinations. Remember, N choose X, and then P power of X and Q power of N minus X. So I think it's a good refresher of what we just did in the previous chapter. So now I'm going to need to calculate it twice and then add, right? So for this matter, I would say there is no real need for the story of the section 5.6. So I go combinations 6, comma 0, because it's a parenthesis. And then P, which is 0.1 to the power of 0, and Q, which is 0.9 power of, what's that, 6 minus 0. And then why do they put 6? I'm just wondering how they get 6. N is 50. Who told me it's 6? Say, Alex, you need to concentrate. There's no 6. No, why did I put 6? Just something happened. Something is not working properly in my head. So one of the wires need to be, I guess, checked out. It's 50, right? 50. I'm not sure why 6. Where I saw the 6. 50. It has to be 50. Simple size. Yeah. Okay, so that's one with 0. And the second was the chance that out of my 50 bolts, 1 is going to be bad. So I have now 1 I put here, and then I go 0.9 power of 50 subtract 1. Okay. Let me use a calculator and do this twice and then add the results, right? Standard procedure that we already mastered. Did you forget it already? See, things that happens that people forget. So you go combinations, right, as functions, and then back to main. So enter the rest, 50, comma 0, and then parentheses times 0.1 to the power of 0, which is 1, but I'll still put it 0, and then times 0.9 raised to the power of single power, the symbol, right? And then in parentheses, I go 50 minus 0, or just 50. 50 minus 0, so I'll just enter that the way we used to do it. So it says, Alex, you entered something in here, so that I misentered, I guess 0 has to be. Okay, so let me clean this a little bit so you better see it. So it looks like we have one calculation performed. So this is really a problem from chapter 4. But my goal is to still do it in order to show you, to confirm that approximations are good. So what's 0.005 approximately, right? 0.005. And then the other piece Now to calculate, we used to just added the calculation. So now I choose 1 in the place of that 0. Now I put 1. That's 50 minus 1. So once you enter one of those, it's becoming pretty straightforward. Now, to be consistent with the previous entry, that was 3 significant digits, I will round it to 0027 or 29, right? I need to increase by 1. 000, actually 29. So when I put these two together, when I add these numbers, I'm going to get approximately 9 and 5 is 14, and then it's 3. So the chances are here, and what I care is to subtract these chances. So to subtract that probability that x is less than 2 from 1, right? We used complements. So 34. Now, since I subtract from 1, so point what? 6 here, and then here's 6, and here's 9. 966. So that's the chances that there be more than 2 defectives, at least 2 defectives, 96% chance. So definitely this shipment is going to be rejected because they test so many of these bolts. So the more of them they test, the more chances that they're going to reject that shipment. So that's the way we used to solve this. But now I want to solve this way, the new way. So how to do that? Well, I need to use approximation of my numbers that greater than or equal to 2, the probability. So I put 2, I put surrounding it 1 and 3. So that's standard, always surrounding numbers. And now it's greater than or equal to 2, so I need that continuity correction. See, at this stage, I don't really care for the answer, but I just want to show you the process and see if we get close enough to what we produced. So looks like I must be right in between of 1 and 2, which is 1.5. So instead of using probability x then greater than or equal to 2, I have to use probability that x is greater than 1.5. And this will enable me to use the z-score process and everything, the one that we already mastered. So if I get 1.5 somewhere here, and I need the area to the right, so this is going to be my x that I need to convert to the z-score, right? Which is again x minus mean over sigma, and in our case, mean and sigma. So yes, I'm doing the problem one more time, but differently. Well, I guess to verify how close we get to the actual answer, because the actual answer is given to me right there. That's my actual answer, right? That's my actual answer. So I need to see what is going to come out now. So we need to use our 2 formulas for mean NP and for standard deviation, which is a square root from NPQ. So please notice these 2 formulas you use when you use continuity corrections. So when you the 0.5 thing. So NP, what is N? 50. What is P? 0.1. Okay. Square root from 50, which is multiplied by 0.1 and multiplied by Q. And we already saw the Q was 0.9, right? We used it here, Q 0.9. Well, let's get our z-square. So these are parentheses. So need calculator. Let's get a calculator and get the z-square. Okay, so 1.5. I subtract 50 times 0.1 in the parentheses, and then divide by square root. Okay, so just a little bit more time left. I know you're probably already getting tired of all that, but just to finish with all this comparison process, so I got z-score minus 1.645, I think, right? So negative 1.645. Well, 165 approximately. We just need hundreds. And again, I need all that because we convert this x to z, and that's negative 1.645. That will be able to give us this same area to the right, and that's coming out of the tables. So now it's negative z. Well, need to scroll it up a little bit. Positive z, now I need negative z-score because areas are always given to me in terms of from the left, right? Okay, so 1.6 was a negative sign, and then 0.5 is from my column. So as usual, row in the column is under 0.5, and looks like that's the area. I see, Alex, that's your favorite asterisk here. Yes, but right now I don't need it because right now I have z-scores, so I just find the area. 0.495 is here. 0.0495. That will help me to get my area, right? The one I need on the other side, the answer, which is going to be subtract, reproduced when I subtract from 1, 0.495. And let's see what we're going to compare with the answer produced in this case, right? So let's see, it stands with 5, then it's a 0, then it's 0.95. So this is the answer I produced doing approximation. It's approximation by normal distribution, my binomial distribution. So 95% is what I produced, but the reality is 96.6%. It's close. It's not exactly the same because it's approximation, but they say it's good enough approximation. They say it's good enough. So, of course, the exact answer I produced the old way because, well, we just needed to do the twice calculations, use formula twice. But in the case, if you need to do it so many times, use the formula 40 sometimes, it is good enough approximation. But of course, it's better if you use binomial formula. But if you can't, approximation is good. That's the point. So we're pretty much done with the chapter. It was a interesting chapter 5 that introduces us into the whole story of normal distribution and how we can use it everywhere. Section 5.7 turns out is also going to be disregarded because that's actually dealing with so-called regression line. So regression analysis, it's also in this textbook, but later is done in very detail, and we're not gonna get there, so we just don't need it. So next time we're gonna look at deeper research of all that. So next time we'll be able to see what if you do work completely on your own. So, for example, you're trying to find some inferences about the population and you have no idea how to start, what it's mean. Because usually they give us population mean, right? They were saying population means, let's say babies, they have 50-50 or some other things. So what if you have absolutely no clue? You're studying some temperatures on the planet of Mars, you have no idea what temperatures there are. So you need to somehow estimate. And that's exactly what we're going to do. Estimate. So we're going to be able to see how statistically you can estimate so you can get what you need, the measurements, and then you will be using the process that we already mastered with all these tables and stuff. So how to start, how to get the estimate if you don't have one. Let's say if they keep it secret, they don't know. So how you can do that. So that's a whole different story, but it is very tightly related to what we've been doing. So I'm sure that next week will keep you excited, and then you will be able to do your own projects if you really need to do one. And whatever your major is, you can just do some estimate and calculate things statistically and amaze your boss at the company, so might get a raise because you will be able to prove things statistically. And that's, I think, very exciting. So let me then stop recording. So I'll let you go.